Well, good morning. And as you can see, it's a little bit of a surprise that I'm speaking first today. Brian couldn't be here, so at least I'm talking on a topic that Brian has worked on a lot. Many of you that know me have commented or asked, why are you here? Why are you giving a talk? You are not a modeler, and that is still true. Though CSDMS and Land Lab played a really important role in my research and in my teaching, using the modules and bothering a lot of your staff to help me figure stuff out as a newbie. Oh, and I should mention Annie Thompson, who's here, my co-conspirator in putting this together, but she never got a chance to see the talk, so it's all my fault. She has a nice poster for you, I think, tonight. All right, so the topic is how do rivers cut their way down through rock? And one of the things they have to do is they don't only have to cut their way through rock, they got to transport all the sediment away. Sediment can provide tools to increase erosion. I'm not going to actually talk about today. Today, in many environments, the role they play is by blanketing the bed and inhibiting erosion. So this is something we've actually known about for a long time. Gilbert talked about it back from his work in the Henry Mountains. And Alan Howard kind of nailed the problem about 1980, describing in general that you can have a whole slider between what we call detachment limited situations, where the incision into the evolution of the bedrock channels is all about eroding the rock. So those are cases where the sediment transport capacity is way higher than the sediment supply, so it's generally a clean bed. At the other end of the spectrum, the sediment transport capacity is about equal to the sediment flux, and you get a transport limited system. So we're going to look at these kind of problems. And on the detachment limited end, at least those of you that play in fluvial landscapes will be very familiar with the stream power incision models. This is K, an erodibility coefficient. Area A is the drainage area, and S is the local slope. M and N are fixed exponents. So it's been around for quite a while. And then about late 90s, people started worrying about the role of sediment. A lot of inspired by Gilbert's early work and some of Alan Howard's early work as well, to recognize that coefficient of erosion is actually a function of the sediment flux. And this F of QS, Sklar proposed that as you go across that slider of sediment flux is near zero, or the sediment capacity is much higher than the sediment supply, to QS over QC equals 1, we get to transport limited, you would just have a linear decline. So the more sediment there is more it's inhibiting erosion, okay? And so this kicked up a model that we called the linear decline model. Greg and I from a paper in 2002. Nicole had a nice paper looking at this and other models back in 2006, where you have just that linear decline described in that term in brackets. That's what we call the cover term. All right, so with that context, there have been quite a few new models trying to handle what do we do with sediment flux involvement in bedrock incision. And my role, I've never been a modeler, but I'm the one that bugs the modelers, right? So my role has always been okay, let's dissect this. Let's figure out exactly how it works, and let's try to break it, okay? So I'm here to say that I found a way, I broke one of my favorite models, but I know now how to fix it as well. Well, it turns out, all of these models can actually be reworked to spend a little time doing the algebra back into the exact same form as the linear decline model, where I've just made the K in red because it's different in each model. And I got this little F factor that pops in there. That's only one model has something that F factor, and we're going to talk about that. That's the source of its issues. All those same models can also be rewritten into this form that if you're familiar with this literature, you've seen it a lot. So you basically, that bracketed term, that's the cover effect. But you can rewrite those same equations. And you'll have an erosion term that looks just like the stream power incision model, or it is, minus a deposition term. Okay, so all those models can be put in either format. And rather than walking through each one, I'm just going to break all the rules and just have this slide covered in equations. Okay, but I figured this group is the one place I can probably do that. So the PSI-Q model from Davy and Log just has those particular values of that K and that G, following you want it all to call it G. Fastscape G, just a different K, otherwise the same. I guess I should back up and mention, KD is the erosion of rock, KS is the erodibility of the sediment, okay? So it's a big, it's kind of a fundamental adaptation of that Chi-Z model to apply it to incision bedrock. Then Hergarten's shared stream power model. That one has just slightly different values. There's fundamentally difference in the G value, but I'm going to talk about those in a second. Well, then, kind of my favorite model that unfortunately I've been able to break, the space model. It's the best in the sense that it's the only one that keeps track of the role of sediment, keeps track of the sediment separately. How thick is the sediment pile? All of these can deposit if that deposition term is greater than the erosion term, you actually grade the bed. However, in all these models, they treat that aggraded material as if it's rock. It's kind of violating all kinds of stuff. If you had a sediment, if you had an accumulation phase and then reincise it, those models are going to do the wrong thing. Space does track that sediment is more erodible and keeps track of where the sediment is. And so it can be written in the same form. That's the one that took me a long time to figure out. That's kind of obvious when you realize it could be. Complex form for what the K is a much more general K. Now, interestingly, space at steady state collapses to a different looking form. And this is the nature of where you can break it. For transient dynamics, that G, the thing that sets the balance between your erosion and deposition terms, that value of that G, that tells you, are you detachment limited, are you transport limited? For a transient problem, that's controlled by this VS over R. So that's supposed to be the sedimentation rate, the settling velocity, and the rate of rainfall. But at steady state, it takes a value that looks like one of the other models. It's a fundamentally different control on what's happening at steady state and whether you've got transient dynamics. So that's what we're going to dive into to reveal. I do want to start with just a comment on this. Is this slider? What controls that slider? So in many of these models, it's the settling velocity of sediment divided by the rainfall rate, which is kind of nutty. I mean, it took me I really have not been able to swallow this. It's an effective parameter because it does let you go from detachment limited to transport limited. But what does it mean? So if you take that settling velocity as order 1 meter per second, okay, you can argue about the details, but it's something like 1 meter a second for gravel. Rainfall rate, order 1 meter per year. So the value of that is 10 million. And it turns out as soon as it's 100, you're totally transport limited. So all these models, if taken literally, say always, they're all transport limited. We know from observations in the field that's not the case. There's many behaviors that indicate you're somewhere on that spectrum towards detachment limited. So I do think that it creates a false impression because it makes you think rainfall rate really sets, like wetter places are going to be more detachment limited. And I don't think that's true. Or at least we don't know whether that's true. So a more sensible one is the one that comes out of the shared stream power model. The coefficient of erosion versus the coefficient for transport, that's ultimately what works. Okay, so let's just take a look at these. Just a reminder, what is this G value? And it's different for some models. I'm showing you for the shared stream power model that Annie developed, ran that code. And on many plots, I'm going to show you the elevation profile, right? This plot. And then I'll also show you the channel steepness against distance. So the channel steepness is the local slope corrected for the drainage area. And what you see, if I have a low value of G, it's detachment limited, and you can see you have this discrete nick point that goes sweeping up the system, and therefore kind of a stair step, a step function in the channel steepness. Now, if we do the same thing, so this is just a channel starting at a low initial case, increasing the uplift rate by a factor of 5. If I have a mixed case, and this is something we showed way back in 2002, you have an initial nick point move through the system, and you can see those nick points here, or in the KSN, a big step. And then it changes over and becomes transport limited and becomes, if you see, Nicole's nodding because this is stuff she also did in a lot of her modeling to show the ramifications of some of this. And if you just bump that G up to 10, you're almost fully into transport limited conditions, right? So very fundamentally different behavior. So what's happening? This complex figure is trying to capture a lot of things. The fundamental thing that's really controlling, are you detachment limited or transport limited, is that ratio of the sediment flux, the sediment carrying capacity. That's really what it comes down to. That's controlled in these models by the value of G. So the G is on a log scale here, and for just normal, at steady state, it's the black line, and just makes that nice sigmoidal. So you can see once G is as low as 100th, your QS on QC is at 0. At 1, you're at 50%, right? They're about your ability to transport sediment and your ability to erode rock are equal. And once it gets up to 100, you're all the way basically just sediment blanketed. Well, in a transient, what happens, and if you've read some of Nicole's early work, you're going to know this. Let's just do a case of uplift rate increase. What happens, the channel steepens at the outlet, but the whole catchment hasn't responded yet, so the QS on QC goes down, shifts you down to here. So it's effectively the same as if your GH changed during the transient by a factor of 10 for this factor of 10 change in uplift rate. Anyway, so maybe I don't want to belabor that one, but generally, if you increase uplift rate, your system becomes more detachment limited. And if you decrease uplift rate, it becomes more transport limited during the transient. Now, let's look at what goes wrong with the space model. Okay, so in the space model, well, first, let's just look again at that normal case. I'm going to take a case where I use a G value of 100. So it should be fully transport limited. There's going to be no nick points. Okay, and so if I keep the erodibility of rock and erodibility of sediment the same, or I use one of the other models that assume that anyway, I'm going to be on the solid black line. That's one I just showed you on the last plot. And so if I'm at GH of 100, means I pop up there and my QS on QC is near 1, I'm basically transport limited. However, if I use just a factor of 1,000 difference in the erodibility of sediment to rock, which is not an extreme value, I think it should be that or more, then I can be right there. And that same thing is going to be transport limited, but have only 10% cover of sediment on the bed. So everything you see in the field is going to look like a detachment limited system, but it's still going to behave in a transport limited way. And I've kind of got a lot overloaded in here, so it's basically like shift that all over to there, as if the G value is 1,000 times less. I'm not going to belabor this, show it a number of different ways. I can let you guys look at that. But to finalize on this, I know I'm blown through that. I spent so much time building those animations. But of course, I overloaded my talk, like anyone's always, right? But anyway, the trick is that there's a G value that you set that sets whether it's transport limited or not. And then G times the ratio of KD to KS, that dictates how thick the sediment is and what the QS on QC ratio is. So you break the link between those two that intuitively should be there. So let's look, there are some actual consequences of this. Even at steady state, there are consequences of this. So this is a steady state where I just have an uplift rate boundary right there between a low uplift and a high uplift upstream, okay? And if we just look at the upper plot on here, this is a case where I left sediment and rock erodibility the same. So space and other models like the shared stream power model are identical, okay? Now space, additionally, the red line is the top of the bedrock. So it shows you the thickness of sediment, and I've just exaggerated it so you can see it in this plot. So it's thick sediment downstream, so all that extra erosion upstream, right? Now, if I just keep everything the same, but make KS more erodible than KD, that just changed the slope. So I've adjusted things so I have the same slope in the upstream part. The slope downstream is way less because that KS greater than KD gives me basically a high transport coefficient. So I got low sediment flux, got a thin alluvial cover, and a much lower transport slope. So it's a completely different channel profile, completely different relief in the whole catchment because of that disconnect happening there. Okay, now, other thing I want to test to really show you where it really breaks is, if you remember this case I showed you before, for a mixed bedrock channel, subject to an increase in uplift rate, there should be an initial nick point that covers about half of the change in channel steepness, and then a really diffusive gradual increase you can see on both those plots. So let's imagine a scenario, one that Nicole and I actually struggled to model a long time ago, of initial low relief channel that has a thick pile of sediment. And what happens when I then trigger a pulse of uplift through that? So I'll make a 200 thick meter pile of sediment, and I'm going to put it through that same process. So here it is. I start it, right? I'm incising into 200 meters of sediment. It's got to be transport limited. But in the space model, if I had G at 1, it's going to behave like a mixed model, even though it's incising through rock. So it gives you that initial Nick point response. And then it does this is just the first 10 time steps, and then the next time steps, does a really wacky thing of where the channel, you get this downstream, this is going from blue to red through time across with time. You've got a Nick point sweeping downstream, and that's as the rock is getting almost exposed to the surface as you're stripping the sediment off, and starts to change behavior so that it's, anyway, it's a really bizarre little response. And then when the rock is finally exposed at the outlet, then you get a Nick point sweeping up through the system of it steepening up. So kind of crazy behavior that happens in this model. So let's just pop forward and we can fix this by, first off, I can achieve it's the same plot I showed you before. Let's zoom in on here, and I'm going to fix all of the other models by adding the ability to track sediment depth. First off, so it's just a plot showing you the black lines on top are the shared stream power model, now with a component, an element added to track the sediment thickness, and it matches space exactly where Ks and Kd are equal to 1, are equal. That's my boundary between those two. Now I can force it in a little transient where I step the uplift rate boundary downstream, do a little crazy thing. I'm of course, way out of time. But the thing I just want to emphasize is a complicated pattern that happens. So I move the uplift rate boundary to there. So now I'm moving that sediment, thick sediment up and eroding it off. The two models with no difference between rock and sediment are identical. The black dashed lines are on top of the colored lines. I guess is all you can really see right now. But I can also add that sediment is more easily erodible into this kind of model. And then you'll see, so in this case, the black lines are the case where they were equal. The blue line is the surface in the case where they're not equal. And the red is the bed surface where they're not equal. So in that case, you don't get as much of a step. You're eroding it faster as you carve down into that sediment. Anyway, not enough time to really explain what's happening there, but let's just pop past that. So we can do the same experiment with this other model, which we can do this fix in space, and I've talked to Charlie Shove about that, and we're going to work on that. We start with that same initial low relief landscape, uplift it through the 200 meters of sediment, and the first time steps here, you can see a perfectly transport limited response. There's no nick point in the system anywhere. The channel steepnesses are just broadly increasing, mostly at the downstream end, and then propagating upstream. A very transport limited response like you might expect. And then as soon as you start exposing rock near the outlet, you get a nick point that goes propagating up through the system. And then eventually, oh, this is actually now, so that's all I wanted to show you for that evolution. And this is the sediment depths plotted down below. So in the first phase, sediment depth is just decreasing, especially at the outlet. By the time it's thin enough, that's when you get into the second phase of the nick point actually sweeps up. Anyway, you can have it all and not have any of the problems that were exposed. So I'm out of time. I'll just throw up the conclusions for you to have a look at. And hopefully that was at least moderately amusing to get you started on your day.
Thank you very much, Kelin. we have time for 1 or 2 questions, if there are questions.
So if I'm following correctly, you're varying the ratio of KS to KD, which is sediment erodibility to vapor erodibility, right? But then you're treating the separate variable. Is that correct?
That's correct, because they are separate in the model. Yeah, oh, I should repeat the question. Nicole was asking, you are varying the ratio of sediment erodibility to rock erodibility independently from the G parameter that determines the model is transport limited or not. And yes, and the answer was yes, because that's encoded into space that it has to be that way.
But it's not settling velocity. So you can't like set it like a real settling velocity. Like you were saying, oh, gravel should be 1 meter per second. You can't set it that way. But technically, settling velocity, you would think, would be tied to the KS. So, and this is something that will expand a little bit too. Like you can sort of vary one or vary the other and get similar results, but shouldn't they actually be both varying?
They should be drawn together, and this is what sent me on a year of headaches working with Andy. We knew what should happen. It should be a whole like non-dimensional number. You can either change KS, KD, or you can change VS over R, and you should get the same thing. But then it didn't happen. And it's because of just the original derivation of the model built on the PSI-Q model, that VS over R, sediment velocity relative to rainfall, that dictates the transient dynamics no matter what, independent of that KS and KD ratio. The KS and KD changes the slope, it changes the steady state, sediment flux, all this kind of stuff. So then it just breaks apart and doesn't behave like the way it should. But it's easy if you go back, once you recognize all the models like can be thought of as a variance of the linear decline model. If you kind of go back to the beginning of space and reset, let's define it from there and go forward. Those things will all be linked together and everything will behave beautifully. So I believe a space 2.0 or 3.0, whatever it's going to be, will do all the beautiful things that it does and won't have any of the weird behavior that we managed to squeeze out of it.
But technically, even though they're not, should be varying KS and what you call G, what is settling velocity in the model in the same way, right? Like, shouldn't they, if we increase one, but like,
yes,
you know,
it ought to. Yeah, except it doesn't work because that's what we thought, and we set off down that path that just will everything be fine. But because in the end, if you're running a transient, like a dynamic evolving thing, it's just VS over R. Uniquely, they control it. So that's the thing. But it's easily, well, I don't know if it's easily fixed numerically, but it's easily fixed conceptually.